As Turing explored what machines could compute, another pioneer, Claude Shannon, was laying the groundwork for how machines could communicate, setting the stage for the digital revolution. Imagine trying to build a complex machine that can perform calculations. How would you represent information? Claude Shannon, working at Bell Labs, was wrestling with this very problem. And then he had a brilliant insight: the elegant simplicity of Boolean algebra. This was the key. He realized that Boolean algebra could describe the behavior of electrical circuits, a groundbreaking connection that changed computing forever. Shannon showed that logic wasn't just an abstract concept. It could be made physical, hardwired into machines. Imagine taking pure thought and turning it into a machine-readable format. That's what Shannon achieved. He bridged the gap between the abstract world of Boolean logic and the real world of mechanics of electrical circuits. Suddenly, complex reasoning could be boiled down to simple on-off switches, electrical currents flipping between 0 and 1, forming the backbone of modern computing. But Shannon's work didn't stop there. He realized that everything, numbers, words, images, music, could be represented as binary digits or bits. This became the foundation of computing, artificial intelligence, and modern communication. Every text message, email, video stream, and AI-driven chatbot owes its existence to Shannon's work. It's no exaggeration to say that without Shannon, we wouldn't have computers, the internet, the AI revolution we're experiencing today. But while Shannon gave us the language of computation, how could machines actually learn? If intelligence was just information processing, what kind of system could replicate human thought? Imagine a vast web of tiny switches, each neuron turning on only if it gets the right combination of inputs. Think of decision making like planning a night out. Is your favorite band playing? Are your friends going? Is the weather nice? Each factor acts like a neuron, sending a yes or no signal. A single neuron can't determine your decision, but when combined, they allow for more complex reasoning. This was their breakthrough, showing that neurons could function like logic gates, the same building blocks that power computers. McCulloch and Pitts' work proved two key concepts. Neurons could perform logical operations, meaning intelligence could be expressed mathematically, just like circuits in a computer. Networks of simple neurons could compute complex functions, suggesting that intelligence emerges from structured connections rather than requiring a single thinking unit. This was a radical shift. Instead of programming intelligence step by step, McCulloch and Pitts suggested that intelligence could arise from many simple units working together, the same principle behind modern AI and deep learning. A single neuron or rule is limited, but when many neurons are connected, they can recognize patterns, make decisions, or solve problems. Think of how AI recognizes faces. A single neuron detects edges. A small network recognizes a nose or eye. A larger network identifies a human face. A deep network determines this is your friend Sarah. However, their model had one major flaw. It couldn't learn. The connections between neurons were fixed, meaning the system couldn't improve with experience. Real intelligence isn't just about logic, it's about adaptation. This led to the next great challenge. How could artificial systems learn from experience, just like the brain does? The answer would come from the emerging fields of feedback, adaptation, and control, setting the stage for machine learning and deep learning. Enter Norbert Wiener. While McCulloch and Pitts focused on neural networks, Wiener was thinking even bigger, exploring how systems, both biological and mechanical, regulate themselves and adapt to their surroundings.
Think of a thermostat. It constantly monitors the room temperature and turns heating or cooling on and off to maintain the desired setting. Now apply that idea to intelligence. Why does this matter for AI? Wiener's work showed that intelligence isn't just about processing information, it's about adapting. Communication and control became central to machine learning, robotics, and AI systems that adjust based on their environment. Cybernetics provided a framework for understanding intelligent behavior, influencing early AI research and shaping how scientists designed autonomous systems. This was a crucial leap forward, moving beyond machines that simply compute to machines that could learn and self-regulate. While Norbert Wiener explored how machines could regulate themselves, another visionary, John von Neumann, was revolutionizing the very architecture of computers, laying the foundation for the intelligent systems that would drive AI. Von Neumann's breakthroughs meant that computers were no longer just tools for calculation. They were now programmable, allowing them to store and manipulate intelligence. The stage was now set for the next leap in AI, where machines would no longer just process data, but learn from it. Imagine trying to build a machine that could not only calculate, but also adapt and learn. One of the biggest hurdles was how to store both the data and the instructions for processing that data. John von Neumann, a brilliant mathematician and physicist, solved this problem with his revolutionary stored program architecture. It wasn't just about building a better computer. It was about creating a machine that could be truly general purpose, a machine that could be reprogrammed to perform a wide variety of tasks. Von Neumann's breakthrough? He redesigned the kitchen. Instead of needing a separate machine for every task, he introduced a single multi-purpose chef, the CPU, who could follow any recipe, the program, stored in a shared pantry, the memory, where both recipes and ingredients data were kept together. This flexibility was crucial for AI. Early computers were rigid, built for specific calculations, but von Neumann's model allowed machines to run complex algorithms, making them powerful enough to support artificial intelligence. This became the foundation of modern computing, and by extension, AI. But AI needs more than processing power. It needs to learn. Running calculations isn't the same as adapting to new information. To make computers truly intelligent, scientists looked for inspiration, not in machines, but in the human brain. Donald Hebb, a Canadian psychologist, wanted to uncover the biological mechanics of learning, how experiences physically change the brain, memories form, and intelligence develops. In 1949, he proposed a theory that explained how neurons strengthen their connections through repeated use. This became the foundation for learning in both biological brains and artificial neural networks. His most famous insight? Neurons that fire together, wire together. It's a simple phrase, but it describes a fundamental process. But Hebb didn't just show how connections strengthened, he also proved a second critical concept. Instead of just looking at individual neurons, Hebb theorized that groups of neurons work together in patterns to encode ideas, store memories, and trigger behaviors. Think of a song stuck in your head. When you hear the first few notes, your brain doesn't just process them individually. It activates an entire pattern of neurons that recognize the melody, bringing the whole song to mind. Hebb's theory explained how entire neural circuits store complex patterns of information rather than just single bits of knowledge. Why was this so important for AI? Hebb's principles weren't just about biological brains. They gave scientists a framework for artificial neural networks. The idea that connections strengthen with repeated use became a core mechanism in machine learning, allowing artificial neural networks to adjust their weights over time, learn from data, and refine their performance. The idea of cell assemblies influenced how AI systems organize and retrieve information, forming the foundation of deep learning architectures today. Understanding how learning works was a crucial breakthrough, but theory alone wasn't enough. Scientists needed machines powerful enough to put these ideas into practice. On the other side of the world, engineers were making strides in building the kind of computers that could bring these theories to life. One of the earliest, CyREC, a machine that helped usher in the age of programmable computing. A team of engineers in Australia built CyREC, the Council for Scientific and Industrial Research Automatic Computer, one of the first computers capable of running complex algorithms. CyREC wasn't just a fancy calculator, it was one of the world's earliest stored program computers. Remember von Neumann's idea of storing both data and instructions in memory? CyREC was built on that principle. This meant it could be easily reprogrammed for different tasks, making it a versatile tool for scientific research. It was like having a universal toolbox that could be adapted to solve a wide range of problems, from weather forecasting to analyzing data from scientific experiments. CyREC marked Australia's entry into the computing age and paved the way for the development of more sophisticated machines. But even as computers became more powerful, they didn't operate in isolation. True progress came from the partnership between human expertise and machine capabilities. Nowhere was this more evident than at NASA, where two remarkable women demonstrated the power of human computing collaboration.